This video is about making Schmitt triggers from comparators. It corresponds to section 33.3 of Applied Analog Electronics. Now, there is no requirement in any of the labs in Applied Analog Electronics to make Schmitt triggers from comparators, but there are some bonus points available in the Class D Power Amp lab if you make your own triangle wave oscillator. And one of the easiest ways to do that is to make a Schmitt trigger. So let's take a look at how that works. First of all, I lied. There is a time when we do this circuit, which is almost always wrong on any of the quizzes. Positive feedback here. Okay? When do we do that? Feedback right here. Positive. Well, we do that to make a Schmitt trigger. And that's about the only time we do it, because the positive feedback, that loop, gives us memory rather than the sort of gain control that we're usually trying to get from an op-amp circuit. And the two inputs, VA and VB here, are just like the two inputs of the generic negative feedback op-amp circuit. Depending which way you hook them up, we get different results. We either hook one of them up to a constant voltage, and we hook the other one up to our input. And we get either an inverting or non-inverting Schmitt trigger, depending which way we hook it up. And obviously, if we hook up the input to the negative input, we're going to get the inverting Schmitt trigger. If we hook up the constant voltage there and the input to the VA, which goes to the positive signal, then we have a non-inverting Schmitt trigger. Let's take a look at a non-inverting Schmitt trigger first. Yeah. Okay. Here we've got the non-inverting Schmitt trigger. We have got a constant voltage. This node here is one that, you should be familiar with this circuit. We've got two resistors here that are identical. We've got a little capacitor there to hold the voltage constant. This is exactly the same circuit we've been using producing VDD over 2 as a reference voltage all along. It's going directly into the input of an op-amp, so it doesn't need to have a unity gain buffer or anything. It's just a nice reference voltage of VDD over 2. Well, what does that mean? If the other input up here is greater than VDD over 2, well, we're going to have the huge gain of the comparator, and the output is going to be positive, high voltage, VDD, because we're using a rail-to-rail comparator here. If this input is less than VDD over 2, then our output is going to be 0. So we've got basically the comparator here. What we need to do is figure out what values of Vin up here does the voltage on the positive input there become VDD over 2. And we've just got a voltage divider here. What is V out? What is V in? And when does that become VDD over 2? And that's a circuit we should be familiar with. We've just got two resistors. All right. In one case, we've got V in and ground. And we had, the ground is when the output was low. So this was V out low. And we had a 1 mega ohm here and a 330 kilo ohms here. And we said that this thing had to be VDD over 2. Well, we can just do the voltage divider equation here. VDD over 2 equals 1 mega ohm over 1.33 mega ohms times V in. And let's see, that's about 3/4 here. So multiply both sides by 4/3, and I get VDD times 2/3 equals Vn. So when the output is low, then this voltage, Vn, has got to get above VDD over 2/3. Once it gets above that, then the output will switch high. What happens then? So we've got a similar circuit here. Vn, 330k ohms, 1 mega ohm. And now, instead of V out low, we have going all the way up to VDD here, and it's V out being high. And again, we've got that this is VDD over 2. And again, we can use the voltage divider equation. VDD over 2 is, now we're going to have 1 mega ohm times V in plus 330k ohms times VDD over 1.33 mega ohms. And we can go through the same sort of calculations as before and get that VDD over 2, subtract this from both sides, minus, what's that, 1/4 VDD, equals, again, about 3/4 Vn. And so this is going to give me 1/4 VDD multiplied both sides by 4/3, and I get VDD times 1/3 equals Vn. So we've got our low threshold is 1/3, our high threshold is 2/3. Nicely symmetric. And the reason they're symmetric is actually forced by the fact that we use VDD over 2, halfway between the two output voltages. If you pick that as your constant voltage for this non-inverting Schmitt trigger, then you're going to get exactly symmetric situation here. And these two resistor values selected it to be 1/3 and 2/3. And by adjusting these two resistor values, for adjusting their ratio, you can move those in and out. If you need your thresholds not to be symmetric, about a half, well, then you have to move that middle voltage, the constant voltage, up or down. And it's all fairly straightforward algebra to try and figure out what resistor values will give you the thresholds you want. Okay, so that's it for the non-inverting Schmitt trigger. Let's look at an inverting Schmitt trigger. This one looks a little bit simpler, in that we have one fewer resistor, though the math is actually slightly messier to do, because we have got get a piece of paper here to do the math. We've got to figure out what the Thevenin equivalence is for that voltage divider up there of R1 and R2. So let's go through that now. We had, if I remember right, I think it was 860 on the top, or 820 on the top. Let's get this right. So we had 820 kilo ohms on the top and 560 kilo ohms on the bottom. And we need to figure out the Thevenin equivalent of that. So that means the Thevenin voltage and the Thevenin equivalent resistance. The Thevenin voltage we just get from the voltage divider equation. So it is 0.4058 times whatever that rail voltage was there. And the Thevenin equivalent we get just from looking at the two in parallel. So if I take 560 I get an equivalent resistance of 332.8 kilo ohms. Okay, so now what we've got is a circuit that looks like this, with 0.4058 here, and that's times whatever our real voltage is, going into that positive input. Remember, again, this is the Schmitt trigger, so we do the weird positive input stuff. And this one was 1 mega ohm. And this one was 332.8 kilo ohms. And here's V in. So now to figure out what the threshold voltages are, when does the input cause the output to change, that's going to be when these two things are equal. We no longer have a constant voltage here. We have two different voltages here. One when the input is 0, or when the output here is 0, and the other time when the output is VRAIL. So let's look at those. We have one case with 0.4058 times VRAIL, 332.8 kilo ohms, and down to ground. This is V out low, and this is 1 mega ohm here. So we can figure out what this voltage is just by using the voltage divider equation. So we've got about 3/4 for the voltage divider equation, but we have to multiply that by the input voltage. And I get that this is about 0.3045 times VRAIL. And we can do a similar thing for the high voltage. We're going to have, again, I'll draw it horizontally this time. So we have the 332.8 k ohms and 1 mega ohm. Now we're going to have this at 0.4058 VRAIL and 1 times VRAIL. And we have to take the basically the weighted average of those. So we have 0.4058 times the 1 mega ohm, 332.8 times the kilo ohms times 1, add the two together, and divide by 1332.8. And I get that this is about 0.5542 times VRAIL. So that's our high threshold, and that's our low threshold. When this thing goes above the high threshold, the output will go low, and when it goes below the low threshold, the output will go high. So it's a fairly straightforward thing, again, to do the calculations you need. Picking the resistor sizes is a little trickier to algebra than before, but still not very difficult. So both inverting and non-inverting Schmitt triggers are fairly simple circuits that are easy to do. And remember, I never want to see that feedback to a positive input unless you're doing a Schmitt trigger. Any other situations, it's a complete failure and not going to stand for it. So no positive feedback except Schmitt triggers.